Hi everyone, welcome to this section on dropout regularization and batch normalization. Student, these are the two common techniques which are used in neural networks and deep learning models in order to avoid overfitting. Let's see what we are going to cover in this section. So first we will discuss about the dropout regularization. We apply dropout regularization at the input layer and in the hidden layer of a neural network or a deep learning model. So what happened in dropout regularization, that we drop the units from the different layers of neural network so that neural network could not learn the noise of the data and it could not enter into the overfitting region. Furthermore, dropout regularization also increase the speed of the training and it also increase the generalization capacity of a neural network. The second is batch normalization. So what happened before feeding data to the neural network, we know that we normalize the data. But what happens when we pass the data to the neural network, then when data travels from one layer to another layer, it gets scale due to the activation function. Therefore, in order to reduce the effect of that scaling on the performance of neural network, we need to perform batch normalization. So we do batch normalization in order to reduce the scaling effect on the data when it moves between the layers of a neural network. So we will study both of these topics in detail in this section, and we will implement them in Python with the help of 4 projects. So I hope you will learn a lot in this section. Thanks for listening, and I will see you in the section. Hi everyone, welcome to this lecture. So in this lecture, we are going to learn about the dropout regularization. Now, what happens in dropout regularization? Okay, look at this model. This is a neural network before a dropout regularization. It has an input layer, it has 3 hidden layers, and the output layer. So what we do when we have to apply dropout regularization? So basically, we assign a probability to each node of the layers of neural network. Here, if you see, we have assigned a probability of 0.5 to the each node of the hidden layers or to the input layers of a neural network. So we can apply dropout to the input layer or to the hidden layer or to both layers of the neural network. So here the probability is 0.5. What does it mean? It means that every node in the neural network has equal probability of being dropped during the training. Let's see what happened during the training. So this is the model after the dropout. This is our epoch 1 of the training. We can see that few of the nodes are dropout. They are not taking part in the training and the learning of the neural network. So this selection is random. Random selection means we cannot predict in advance that which of the node will be dropout during the training because we have assigned 0.5 or equal probability to each of the node of the layers of neural network. So this is the situation of a neural network during the training after epoch 1. So what happened after epoch 2? So this is after epoch 2. Now we can see that different neurons or different nodes are selected. Now these neurons are not taking part in the learning and previously different nodes were selected. So every time we run the epoch, different nodes are selected. In that way, the training of the model remains smooth and it will not enter into the overfitting region. So that is the intuition behind the dropout. So dropout doesn't mean that those nodes are not physically connected with the neural networks. It means their activations are forced to 0 or these nodes are not taking part in learning. So here are the important points which we have to remember about the dropout regularization. So basically the unit are not physically out of the model, but their activation are forced to 0. So these units are selected randomly because we have assigned probability to these units. So they are not physically out during the dropout regularization, but the important point to remember is their activations are turned off. Okay, in every epoch, the probability of dropout is same, but units are selected randomly and it continues till the end. So we have already discussed this point that during every epoch, different nodes are selected because their selection is random. Their selection is based on the probability and their selection is random. And this random selection continue till the end or till the completion of the training. Now, another very important point is that we do not apply dropout during the testing. So the dropout is only during the training. It is not applicable during the testing. So what is the problem now? We do not want dropout during the testing. So the problem is the node is higher during the testing than the training. So it means that the scaling factor is not same during the training and testing, because we are not going to apply dropout during the testing. So what is the solution of this problem? So if you see here, testing, all the nodes are taking part in the learning, but during the training, few of the nodes are dropped from each of the layer due to the dropout regularization. So here the scaling factor for the data is not same during the testing and training. So what is the solution of this problem? So there are two possible solutions of this problem. The first solution is scale down the weights during the testing. So that is the problem, or that is the solution which we can apply during the testing. The other solution is scale up the weights during the training. So there are two possible solutions. One solution is applied during the testing and other solution is possible during the training. Let's understand what does these solutions mean. So scaling down the weights during the testing. So during the testing, what we can do, we can reduce the magnitude or the scaling value of the weights by multiplying the weights with 1 minus p. So what is 1 minus p? Since p is the probability of dropping the node, therefore 1 minus p is the probability of keeping the node. So the value of 1 minus p is less than 1. And we know that if we multiply any number with less than 1, its value decreases. So in this way, we scale down the weights during the testing by multiplying the weights of each layer with the factor or with the scaling factor 1 minus p. So this is the first possible solution of the problem. The other solution is that we scale up the weights during the training. So here we can see that this is the training and we can see that there are few nodes which are drop out during the training. So what we can do in order to keep the scaling balanced during the training and testing, we can multiply the weights during the training with a scaling factor q. Here q is equals to 1 over 1 minus p. 1 minus p is less than 1. So if we multiply any number, if we multiply 1 with a number which is less than 1, the value of this number increases. It means q is greater than 1. So the simple thing about the q is it is greater than 1. And when we multiply the weights with a number which is greater than 1, we scale up the weights during the training. So these are the two possible solutions. One solution is available during the testing and other solution is available during the training. So during the training, we can scale up the weights so that the effect of dropout is reduced on the scaling of the data. So in PyTorch, second method is being used, that is scaling up the weights during the training. So here are the important observations about the dropout regularization. So it prevents the neural network to learn more than necessary. When we drop the nodes from the layer of neural network, it stops the neural network to learn the noise of the data. So this is very important advantage of the dropout regularization. Works better on deep than shallow network. Okay, if you have more hidden layers, the performance of dropout regularization will be more obvious. So it works better on the deeper network than the shallow networks. Work better with large data set. We know that for a neural network and for deep learning model, we need large data. So if we have a large data, the performance of dropout regularization will be more obvious. Results in more smooth training. So when we drop out, in that case, our model will not learn any noise or unnecessary thing from the data. Therefore, our training will be smooth. The next point is dropout regularization makes the model less dependent on certain units. So what happens that during the training, what happens, some of the nodes are starting to depend more on some of the previous or on the next node, especially on the previous node. So what happens if that node, if the learning of that node is totally dependent on this every time? So in that case, it will not learn by itself, and its learning will depend on that. In that case, what happen, or what happen when we apply dropout? So when we will apply dropout, in that case, the dependency of this neuron on this neuron will become less, and it becomes independent. So in order to make independent learning to the nodes of neural network, we apply dropout regularization. So makes the model less dependent on certain units. Adding dropout may decrease the training accuracy but increase the generalization capacity of the model. Now, this is very important point. What happens? Suppose that the training accuracy of your model is 95% and the testing accuracy is 90%. So what happened after the dropout? After the dropout, it is a chance that training accuracy reduce from 95 to 90, but your testing accuracy will not be reduced. So dropout may decrease the training accuracy, but it will not decrease the generalization ability of the model. Now, these are the few tips about the dropout regularization. We can start from a low value of the dropout probability, that we can start from the 0.1 or 0.2. So if we start with the 0.2 probability, it means we are starting from the 20%. So 20% means our probability is 0.2 and we are assigning 0.2 probability to each node during the dropout regularization. If that does not work, then you can gradually increase the value of the probability from 0.2 to 0.3, 0.4, and 0.5, and so on. It is more likely to observe better result on a deeper neural network. So dropout regularization is a technique. If your model is performing well, it doesn't mean that you have to apply dropout regularization. It is not a mandatory option. It is not a mandatory method, or it is not a mandatory regularization. It is an optional. So you have to see if your neural network is deeper, it has 3, 4, 5 or more hidden layers. In that case, dropout regularization work better as compared to the shallow network. Shallow network mean the network which is less deeper. So last point is the dropout can be used to input layer as well as hidden layer. So we can apply dropout only on input layers, only on hidden layers, or on both layers simultaneously. So in this lecture, we learn about the important points of the dropout regularization. The important points are that dropout regularization is useful if your model is deeper and if you have a large data set. And the good starting point is that you should start with a small value of the dropout. That is, you can start with dropout equals to 20% or 0.2. And if your model performance does not increase, then you can gradually increase the probability of dropout. So I hope you understood the concept of the dropout regularization. You have understood why it is important and how it stops the model to enter into the overfitting region. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. So in this lecture, I will explain you about the VSAT dataset, because I am going to use this dataset in order to learn the effect of dropout regularization on the performance of neural network. So this is the paper which introduced VSAT dataset. When this paper was published, we get VSAT dataset. So what is inside the VSAT dataset? So here we can see that we have 15 users. From user 2 to user 17, we have 15 users. So this data set was collected with the help of 15 users. Therefore, this is a large data set. And we know from the previous lecture that if we have a large data set, then we can clearly observe the effect of dropout regularization on the performance of neural network. That's why we are going to use this large data set. Okay, so what is inside each user file? So we have 15 users file, and every file is a CSV file. Inside each CSV file, we have ECG data. What is ECG data? ECG data shows the electrical activity of our heart. This is the typical ECG signal. We can see that it starts from some starting point, then it has few peaks, and then it continues its movement. So we are not interested about the shape of the ECG signal and the characteristic of ECG signal. in this particular lecture, basically we are interested in observing the features of ECG signal, because I am going to use the ECG signal with the help of my neural network, and then I will apply the dropout regularization, and I want to see the effect of dropout regularization on the performance of a neural network. So here every ECG data has 256 features. So the length of ECG data in every user file is from 0 to 256. If I include 0 and 256, so that we have basically 257 column in every user file. So the last column, the 256th column, is about the information of the labels or classes of the dataset. So from 0 to 255, including both 0 and 255, we have 256 features in each file. So these are the three classes in a VSAT dataset. We have class 0, class 1, and class 2. So class 0 is considered as a first level of stress. This is second level of stress and third level of stress. For easy understanding, you can consider that first level of stress means no stress, second level of stress means medium level of stress, and third level of stress means high stress. So in VSAT data, basically, we have three classes of stress, and with the help of ECG data, we will classify which level of stress a patient is feeling. So this data set was collected with the help of 15 patients or 15 users, and with their ECG signal, we will classify what is the stress level of each patient. So I am going to implement this data with the help of PyTorch in the next lecture, and I will see what is the effect of dropout regularization on the performance of neural network if I use VSAT data. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. So in this lecture, we are going to solve our project 1 of this section. So basically in project 1, we are going to learn the effect of dropout regularization on the performance of neural network, and we are going to use a VSAT dataset. Okay, so here I am in my course material folder. This is my Google Drive. Click on this course material folder. Inside course material folder, I have three major sections of the course: introduction, supervised machine learning, and unsupervised machine learning. Click on supervised machine learning. Inside supervised machine learning, I have a folder, dropout regularization and batch normalization. Click on this folder. Inside this folder, I have my project 1, dropout neural network on ECG VSAT. So we have VSAT dataset, which is an ECG based dataset, and we are going to see the effect of dropout on that dataset with the help of neural network. Okay, click on this file so that we can open it in our Google Colab environment. So here I am in my project 1 of this section. Okay, for this project, I need PyTorch, I need torch.nn.functional.sf, I need data loader and tensor dataset. I also need train test split function. I need NumPy, Matplotlib, Seaborn, and Pandas. Okay, let's run this cell in order to import all these necessary Python libraries. Now I want to see if GPU is available or not. So I am checking torch.cuda is available or not. So it is true. It means GPU is available for this project. Okay, let's print the device. So device is CUDA, that is our GPU. Since I am going to use a VSAT data which is present inside this folder, therefore we know that in order to read the data from the folder, we need to mount the drive. We need to set the path. Okay, let's mount the drive first. So here we are mounting the drive, and after that we will set a path so that we can import our data in our Google Colab environment. So here you can see that the drive is being mounted, and after that we will set a path. So mounting is being done, and here we have refresh. We have a drive. Inside drive, I have my drive. Click on my drive. I have my course material. Click on my course material folder. Inside, I have supervised machine learning folder. Click on this folder. I have a folder which is dropout regularization and batch normalization. So everything is present inside. If I click on this, I have a VSAT data. Now the problem is if I click on the VSAT data, inside VSAT data, I have these users file. That is from user 2 to user 17. I have 15 CSV file for vset data. Now the concept is that whether I need to copy the path from here or I need to copy the path from here. So we can copy from everywhere. So for the standard technique, what I am going to use, since this is my main folder of the section, dropout, regularization, and batch normalization. So I am going to copy the path from here. So copy the path and paste the path here. And after that, you can run and we can see that the path has been set. If we see the path, it is drive, my drive, course material, supervised machine learning, and the final folder is batch regularization, dropout regularization, and batch normalization. Now I am going to read these CSV file. If we see, we have CSV file here in different order: user 2, user 3, user 4, user 5, user 6. So we have CSV file from user 2 to user 17. So here I have 15 CSV file, and in this cell I am reading all these 15 files. So I can write this code in a single line as well, but that will be a mix or a complex code. So in order to keep things simple and understandable, what I have written, in each line of this code, I am reading one CSV file. If you see here, the command is pd.read_CSV. Here I am reading a user 2 file only, then user 3, then user 4. So similar way, I am going up to user 17. So from user 2 to user 17, we have 15 different users. So these are 15 lines, and each line I am reading a data set. If you see here, one very important thing, that inside this folder, this is our main folder where vset dataset is placed. So dropout, regularization, and batch normalization. In this folder, we have vset folder as well, and inside vset folder we have these user file. Therefore, if you see the path, I have written vset folder, which is inside this folder. This is my main folder. Inside my main folder, there is a subfolder vset data, and inside this folder I have these CSV file. So therefore, path is vset data, and then inside this vset data I have these users. Okay, now run this cell to import all these CSV file in my Google Colab environment. That is, I am going to import the data which is in the form of 15 files. So I have successfully import my data. Now let's check any of the file. df2. df2 is the file or a data file, or it is a CSV file for user 2. Similarly, df3, 4, 5, and up to df17. Let's check the head of df2. If we see the head of the df2, definitely in head, we have 5 top samples. But this is the important information. We have 256 columns from 0 to onward. We have 257 column. If we see, the last column is 256 and the first column is 0. So including both 0 and 256, we have 257 column. The last column is starting from the label. It has 0, 1, and 2, 3 different kind of labels. So therefore, we can see that in each user, we have 257 column. If I want to check user 3, df3, and if I click it again, if I run this cell again, now we can see that for user 3 as well, we have 257 column. If I want to see the last user, which is user 17, if I run this cell again for user 17, we can see that we still has 257 column. So for every user here, we have 257 columns, and the last column of each user represent or shows the class to classify. Okay, now what I am going to do here is, if I want to see the whole shape of df2 here, so df2 has 5,798 sample and 257 column. Now what I am going to do now, I am going to concatenate all these 15 users in a single file so that I can create a big data which I can be used with my neural network in order to see the effect of dropout regularization. So if you see here, I am using command pd pandas.concatenate, and here I am concatenating all these 15 files. If you see here, when I read the data, the header is equals to none. I do not want to give name of to any features because we have 256 features and in total we have 257 column. So if you read the file with the help of pandas and you put header is equals to none, so there will be no header at the top of each feature. They are just the serial number 0, 1, 2, 3, 4, 5, 6 up to 256. Okay, so now I am going to concatenate my 15 data sets, that is from DF2 to DF17. Let's run this cell to create a big data. If I want to see the shape of a data, now we can see that we have 90,630 samples and we have 257 column. When I see the shape of DF2 only, I have only 5,798 sample. When I combine all these users to create a big data, now look at the number of samples. They are 90,630 samples. Okay, and we have 256 columns in total, starting from the 0 column and the last column is 256. So including both 0 and 256, we have total 257 column. Okay, so the last column is 256. This column is about the classes. Let's see how many classes are there and how many samples are in each class. Let's run this cell. Data 256 means I am going to observe the 256th column of the data and how many different values are there. So we have 1, 2, and 0, 3 classes. So we have 48,000 sample in class 1. We have 27,244 in class 2, and we have 15,239 samples in class 0. So we have different number of samples in each class, but we do not need to worry about. The reason is the minimum sample in each class is 15,000. If we had like 40,000 here and only 2,000 or 1,000 in other classes, then there is a point of worriness. But here, even the classes seems to be unbalanced, but even the class which has less number of samples, those samples are more than 15,000. So we do not need to worry about these different numbers. Okay, here I am going to check how many classes I have. So I have already know about that we have 3 classes from 0 to 2. So if we want to check, this is another way of checking the class. So the command is, this is my column 256.value counts and how many unique values. So I am going to use np.unique function and how many different unique values, and here is the length of the unique value. So we have 3 different unique values and we can see that 0, 1, and 2. So therefore the length of the unique value is 3, that is 1, 2, and 3. Okay, now we have understood about the data set. We have combined the data from all the users and we have created a big data. We have seen how many classes are there and how many samples are present in each class. Now it's time to extract features and labels and to apply neural network. Okay, so for feature, I need everything except the last column. So here I am extracting every column except the last column, and with the dot values, I am going to transform these features into NumPy array. Similarly, for my labels, I need only last column, and with values, I am transforming the values into NumPy array. Okay, let's run this cell to extract features and labels. And here I am going to perform train test split. So I am going to use 20% of data in a test and 80% data in a training component. Okay, now these are again few important steps when we use PyTorch. The first step is we have to transform all the training and testing data and the training and testing labels into PyTorch tensor. So here I am transforming my training data into PyTorch, my testing data into PyTorch, training labels and testing labels into PyTorch tensor. Here I am transforming this data and labels into PyTorch dataset. This is very standard stuff. We have seen this so many times now. And here I am pushing the PyTorch dataset into the data loader so that I can shuffle the data. I can set the batch size. So here for this particular project, I am going to use a batch size of 32. This 32 batch size is both for the train loader and the test loader. We can see that we are going to use. And here drop underscore last is equals to true. We know about this important step that when we train the model with the batches, we drop the last samples if they are less than the batch size. Okay, let's run this cell to perform all these necessary steps. Let's observe the batches of training and testing. So here I am going to run a for loop on a train loader. And after just one iteration, I am breaking the loop and I want to see the shape of my features and labels. So we can see that we have batch size of 32 and we have 256 features. And here we have 32 labels. That is for each sample in the batch size, we have a label. Similarly, if I want to see print Y here, so we have these 32 labels in our train loader for the first batch. Similarly, we can check our test loader as well, since we are also testing the model with the help of batches and we are passing a test data in the form of batches. So we can see that we have a batch size of 32 for test component as well, and we have features 256. Okay, so this is the observation about the data loader both for training and testing. Now it's time to create the neural network. First, I am going to create a neural network without dropout regularization. First, I am not going to apply dropout regularization. So this is a simple neural network. If you see the neural network, so I am going to use a class in order to create the neural network. So this is my class and I am calling it neural net. Okay, so this is the standard syntax. Here is the definition of my input layer. In my input layer, I am starting with 256 here. The reason is that in this dataset, I have 256 feature. So the designing of neural network will start from the number of feature. This is 512. So the output feature of my input layer is 512. So the first hidden layer starts from the 512 and the second or the output feature of the first hidden layer is 256. Then second hidden layer starts from 256 and ends at 128. This is my output layer or the classification layer. It starts from the 128 and here is 3. So 3 here is written because we have 3 classes in our data set. We can confirm from here that we have 3 classes in our data set. So this is very standard stuff and this is very easy to design neural network with the help of class. Now this is a forward pass. Forward pass means what we want to do with our data. So our data is X here. So first this data will be passed from the input layer and then I will take a ReLU. So in this line, basically I am going to perform 2 steps. First, I am processing or passing my data to the input layer and then I am taking a ReLU of the data. That is, this is my activation layer. Then this data I will get from the ReLU layer. Then this data will pass from the first fully connected layer. Then I have the second activation function. Then this data will pass from the second fully connected layer and I have this activation function. And finally, this will pass from the output layer. So this is my forward pass, that is starting from the input to the output. So this is the forward function. So we have seen this now many times, especially in the previous section of the course, which was neural networks for the classification. Now run this cell to create the class. And here I am creating the model instance and setting the parameter. So I am calling my model as a model. This is neural net. This is the name of the class. So this is the instance of the model. Here I am setting the loss function. And here is my optimizer, which is stochastic gradient descent. Let's run this cell to create the model instance and setting the parameters. Now here is the important position or important cell of this project. I am going to train and test the model. Now, student, this is very standard stuff. We have seen this many times in the previous section of the course where we apply neural network for the classification. Here I am going to train my model for 25 epochs. Here I have initialized the loss because for every epoch I need the value of loss. Here is my training and testing accuracy. I need training and testing accuracy for every epoch. Therefore, I have set the empty list here. Here I am looping over the epochs, that is for 25 times. I am putting my model for the training, that is training mode. Here I am putting my model to device, that is very standard stuff, that is to GPU. This is my batch accuracy and my batch loss. Because we know whenever we train the model in the form of batches, there is a batch loop inside the epoch loop. So there is a batch loop for X, Y, and train loader. Then I am putting X to device, that is GPU, Y to device. Here I am passing my X to model. I am getting the predictions. Then I am comparing my predictions with my labels to get the loss. And these three steps are very important, and we know about these three steps. These three steps perform backpropagation. Okay, here I am appending the loss which I calculate here to my batch loss list. Okay, then I am placing those ypred and y which I have calculated back to CPU. Here I am calculating the batch accuracy. So after calculating the batch accuracy, I am appending the batch accuracy to this batch accuracy empty list. Okay, so here now I am out of the batch loop. So here is my training accuracy. So training accuracy is the average accuracy of the batch accuracy, and it is training loss is the average of the batch loss. Therefore, I am taking np.mean here and np. So this is my total training. So from here to here, this is a batch loop. And when we come out of the batch loop, this is back to the epoch loop, which is here. So this is very standard stuff. I explained you in detail in the previous section of the course, that is neural network for classification. Especially when I designed a neural network for MNIST data, I explained this code very detail, and I told you there that this is a standard stuff and we are going to use this code in every classification problem. Here is my testing part. So I am putting my model to evaluation mode. Since in testing I do not need any gradient or backpropagation, therefore I am putting gradient to false. Here is my test loader. I am extracting my testing features and labels, and here I am passing it to the model. I am getting the prediction, and this is my test accuracy. So I am running it for 25 epochs. Now, student, this data set is large, as we have already seen. It has 15 users. So I am not going to run this here. I have already run this for 25 epochs. We can see that the last epoch is not shown because from 0 to 20, it is 21 epochs, but it has run for all 25 epochs. What you can do, student, you can click on this, you can run this cell, so it will run. Since it will take around 15 or more minutes, therefore I am not running it now. I have already run it and I am going to show you the result. So we can see that during the first epoch, our loss was near to 1, that is 0.97. And at the end, we have a small value of a loss. When I plotted this loss and when I plotted the training and testing accuracy, these are my results about the neural network on VSAT data without the dropout regularization. So my training accuracy is 80.32 and my test accuracy is 62.5. So we know how to plot these visualization. We have already learned about this code in the previous section where we implement neural network for the classification. So we have done now. What we have done, we have halfway through. It means we have applied neural network here without dropout regularization, and our training and testing accuracies are here. Now it's time to create a neural network with dropout regularization and see if the model improves or not. Okay, so here I am again going to create a neural network, but this time with dropout regularization. I am calling it neural net 2 now. Rest everything is same. This is the new thing, self.dropout. So I am going to apply a dropout after the first hidden layer or the first fully connected layer. Then again, I am going to apply dropout after the second fully connected layer. The important thing is here, my dropout probabilities are very small, that is 10%. So I am going to start with the smallest value, because if you remember in the previous lectures on dropout regularization, where we discuss about the tips of applying the dropout regularization, that we should start from the small value. So if my performance model will not improve with this 10% dropout, then I will slowly increase the value. Okay, so I am starting from the very small value, which is 10% or 0.1. Here I can see how to put a dropout in the forward pass. So this is my input data. I am passing it to the input layer. Then I am calculating the ReLU. After that, this is my first hidden layer, which is a fully connected layer. And after that, I am passing it to the activation function. Here you can see that after the fully connected layer and a ReLU, I am applying a dropout. So this dropout is after the first hidden layer, and this dropout is after the second hidden layer. So we are applying a dropout here only for the two hidden layer, and the percentage is 10%, or the dropout probability is 0.1. Let's run this cell to create a neural network with dropout regularization. Now these steps are same. I am creating the model instance. Now my model is neural net 2, and I am calling my model 2 here. This is my loss function, and this is optimizer. And here you can see that again, my model is model 2. I am again setting everything same here. I am again going to run this for 25 epochs for the training. And we can see that there is my model 2. I am putting my model in training mode. Here I am pushing my model to device, that is GPU. And here my training is start. These are the important step of the backpropagation. So all these steps are same. There is no change. Every step is same, except we have model 2 now. If you see here, we have model 2 now rather than model. So model 2 is the model with dropout regularization. When I train it for 20 epoch, and when I plot the performance, we can see that our test accuracy has improved. So look at the test and training accuracy here. The test accuracy is 68.75%. The train accuracy is 77%. If I go back and see, my training accuracy was 80 and testing was 62.5. So here the testing accuracy has improved, but training accuracy has dropped. So this is an important observation. If you see the lecture on dropout regularization, I told you in the observations about the dropout regularization that you might get a decreased training accuracy after the dropout regularization, but there will be no decrease in the testing accuracy. And this is actually, and this is really about that observation. We can see that our test accuracy has improved. So the generalization capacity of the model has improved. Its training accuracy dropped from 80 to 77.6%, but its testing accuracy has improved from 62 to 62.5 to 68.75%. So we observe that the generalization capacity of our model has improved with the dropout regularization. Now it has the ability to perform well on the unseen data when we apply dropout regularization. So student, in this project, we learn how to apply dropout regularization. After learning how to apply dropout regularization, we observe the effect of the dropout regularization, that there is an increase in the generalization capacity of our model. Now it is performing well on the testing data. So we apply the dropout regularization only on the hidden layers here with a very, very small probability of 0.1. So what you can do, you can change the probability and you can run this code again and see the effect of the dropout regularization. It is not necessary that if you increase the dropout probability, you get more better performance. Your performance may get worse. So again, this is a very tricky thing. Therefore, you have to start with the small value of a dropout, that is 10%, then 20%, then 30%. And you have to check which dropout is better for your model and which dropout is better for your dataset. So in this project, we learn how to apply dropout regularization on the neural network. We used VSAT dataset. VSAT dataset is a large dataset, not in terms of feature, but in terms of samples. We have 256 features in this dataset, and we have data collected with the help of 15 users. And when we combined all the users, we get a large data set. So I hope you understood the concept of dropout regularization. I hope you understood how to design a neural network with dropout regularization. Thanks for listening this project, and I will see you in the next lecture. Hi everyone, welcome to this lecture. So in this lecture, we are again going to learn how to use dropout regularization with the neural network. But this time, we are going to use a different dataset. That is, we are going to use custom images dataset. So here I am in my course material folder. Click on this course material folder. Inside the course material folder, I have supervised machine learning folder. Click on this supervised machine learning folder. Inside this folder, I have dropout regularization and batch normalization folder. Click on this folder. Inside this folder, I have a folder I have a file, basically project 2 dropout neural network on custom images. So this is the project 2 of this section, and this is the project which we are going to solve in this lecture. Click on this file so that we can open it in our Google Colab environment. So here I am in my project 2. Now, student, in this project, I am going to use custom images. We know that custom images are images which are present in the original form in a folder. And we know that when we have custom images, we cannot use train, test, split function in order to create the training component of the dataset and the testing component. For this, we need a split folder function. Therefore, the first step of this project is that we are going to install a split folder function here. Let's run this cell to install a split folder. Here we can see that the requirement has already been satisfied, so it is installed. Now it's time to import all these important Python libraries. So these are all the standard libraries which we have already seen. Here the new thing is that we are also importing a split folder after we have installed it. Let's run this cell to import all the Python libraries. Now it's time to check which device is available, whether it is CUDA, that is GPU available, or the CPU available. So we can see that we are available with the GPU. Now this is another important step. Here we are using transform.compose in order to convert the images into PyTorch form. We know that when we have images, we cannot use a function torch.tensor in order to convert it into PyTorch tensor. Torch.tensor is helpful if we have a data in the form of NumPy array. But if we have a data in the form of images, we have to use this transform.compose. And here our transform is to tensor. That is, we transform images to the tensor. Furthermore, this function will also normalize the images. Okay, let's run this cell. And now, in order to save the time, we have already mounted the drive and we have already set the path. Okay, so the drive has been mounted, the path has been set. We can see that the drive has been already mounted, the path has been set. If we see the path, we can see we have a drive. Inside the drive, I have a my drive. Inside my drive, I have course material. Here I have supervised machine learning. Inside supervised machine learning, I have dropout regularization, and here I have a folder, a circle cross, which I have to read. So I have copied the path from here and I have pasted it here. Okay, let's run this cell again to set the path. Now it's time to read the folder. So we are going to perform many steps in this cell. Let's run this cell first and then we can understand it. Okay, if we see that we are reading our data folder, circle cross. After reading the folder, we are creating another folder here, output. Since we have already run this cell, we can see that the output folder has been created. Okay, so in that output folder, we will have two folder, that is for the training component and a testing component. So we have set the ratio. Our 80% data will be used as a training and 20% data will be used as a testing. Here we have written move is equals to false. That is, we are not moving our images from the original folder to this output folder, but we are copying it. Okay, so if I see this output folder now, the splitting has been done. We have a training component and we have a testing component, which is called here as a validation component. Okay, if I click on the training subfolder, which is inside the output folder, inside the training folder, I have the categories, circles, and cross. These are the two labels of our custom image dataset. And I have the validation folder, which also has two categories. So this is the form which is acceptable for the neural network when we have images in the folder, that is, we have a custom images. Okay, now it's time to transform the folder into the tensor dataset. So we have training component inside the output and we have a validation component inside the output folder. So we are transforming them into the tensor dataset. Since they are inside the image folder, so this is the standard method of creating a tensor dataset if we have the image folder. So the command is datasets.image folder, and dataset for image folder. This is for the training component and this is for the testing component. And here we are applying the transform on both the training and the testing part of the images, so that we can transform them into the PyTorch form, and we are also able to transform them into the normalized form. Okay, let's run this cell. After that, we are passing this tensor dataset into the data loader. Inside the data loader, we have the advantage to shuffle the data, and we have the advantage to set the batch size. Here, I am setting a batch size of 32, both for the training loader and for the testing loader. Here, I am printing the classes, and here I want to see how many training data and testing data is available. So if I run this cell, I have 15,900 training images and 401, 1,599 training images and 401 testing images. And I have two classes, circles and crosses. Okay, now it's time to observe the images in our batch. So we have 32 batch size. Okay, now I am applying a for loop on my training loader, and after first iteration, I will break the loop and I will see the shape of the images. So shape of the images means images are my feature. If we see a data loader here, we have a batch size of 32, and this is the size of each image. So our size of the image is 116 by 116, and this 3 represent that this is a 3-channel image, that is, it is a color image. Now, student, the problem is here, the data is in the form of 4D. We have 4 dimensions here in train loader, but for neural network, we need 2D data. Therefore, when we start training, we will transform this 4D data into a 2D data. Let's see few labels here now. So we have 32 labels because we have batch size of 32. Since we have 32 samples, so we have one label associated with each sample. Now here we are going to print the labels and classes, and we are also going to see some of our images. So we can see that this is our custom image dataset. As I mentioned, we have already worked on this dataset in the previous project, in the previous section as well. So therefore, it will be easy for us to use it again in this section. So we have two kind of categories, crosses and circle. We can see that we have different shape of crosses and circle. Okay, now it's time to create our first neural network of this project, that is without dropout regularization. So without dropout regularization, this is the same neural network which we used in the previous section. And here I am creating it with the help of sequential method, that is nn.sequential. So neural network always start with the number of features present in the dataset. We have images of size 116 by 116. We have 3-channel image. Therefore, the total features available are 40,368 if I multiply these 3 values. So my neural network designing starts from this value. Then I have output features 2048 for this input layer. Then my first hidden layer, second hidden layer, third hidden layer, fourth hidden layer, fifth hidden layer, and sixth hidden layer. So between input layer and the last layer is my output layer. I have 6 hidden layer. So this is a very deep network. This is a very deep neural network. If you see the last layer, which is the classification layer or the output layer, the 2 is written here, which shows the number of classes. Okay, let's run this cell to create the model. So here we can see the summary of our model. We have input feature, we have first hidden layer, second, third, and after each layer, we have a ReLU as a activation layer. Now it's time to train and test the model. So student, I am going to train it for 41 epochs. And this is again a very standard stuff. That is, we know how to train and test the model. We have learned how to create the code of training and testing. So this is the same code which we have used in the previous project and also in the previous section of this course. So the important step is that here I am transforming 4D to 2D. We know that in our train loader here, our data set is in the form of 4D. So we have to transform it into 2D before passing it to our model. The same I am doing with the testing component here. You can see that I have transformed these 4D data into 2D by multiplying last 3 dimensions. So I am running it for 41 epochs. So when I run this for 41 epoch, this is my training accuracy and test accuracy. My training accuracy is 90.24 and my test accuracy is 96.88. So this is without dropout regularization. Now it's time to create neural network with dropout regularization. For dropout regularization, I am going to use a class in order to create a neural network. So the keyword is class, and I am calling it as a classifier. Okay. So this is my input layer. So everything is same as that of a sequential network which we created here. Only thing is that we have added the dropout layers. So we have a large number of layers here. So after every layer, we have a dropout layer, which we have already seen in the previous project, that how to add a dropout layer when we create a neural network with the help of a class. The difference is here the dropout probability is 20%. In the previous project, the dropout probability was 10%. Here I am again applying dropout to each layer. Okay, so if I run this cell, I will be able to create the neural network with the dropout regularization. Here dropout percentage is 20%. That is the probability of dropout for each node of the layer is 0.2. Now, again, here I am creating the instance of a class. I am calling it model2, and here I am training and testing the model2. So the model2 is with dropout regularization. When I run this, I will get the training accuracy 88.46 and test accuracy 96.88. If I go back and see what was the performance without dropout, so the performance is that test accuracy was 96.88 and training accuracy was 90.24. If we see here, our training accuracy has dropped a bit, but test accuracy is same. Now the question is whether the performance has improved or not. Now, student, I have intentionally selected this data set so that we can get some different observations so that we can discuss more about the dropout regularization. Now, student, we can see that here the testing accuracy has not been improved, but the training accuracy has reduced. So reducing the training accuracy is one of the most important observation when we apply dropout regularization. Now we can see that even with the less training accuracy, our model is able to get the same test accuracy which it achieved without dropout regularization. So we can see that the generalization capacity of our model has increased, even though the test accuracy has not been increased. But with the decreased train accuracy, this model is still capable of getting the same test accuracy. So this is the improved performance because this dropout regularization has improved the generalization capacity. How it improved? Here, model need train accuracy of 90% in order to get the test accuracy of 96.88%. But here, model need less training accuracy in order to achieve the same test accuracy. So the generalization capacity of the model has improved and it will perform well now on the unseen data with the help of dropout regularization. So in this project, we learn again about the dropout regularization, but we select a very different data set, which is the image data set, and that data set is in the form of crosses and circles. That is, we had two image categories. So we trained the model for 41 epochs with regularization and without regularization, and we observed that our model has improved a bit. Its training accuracy has decreased, but its generalization capacity remains the same or it has slightly improved. So I hope you understood the concept of dropout regularization, which I explained in this particular project. I intentionally select this project where we get the same test accuracy with the reduced training accuracy. So I hope you understood this concept. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. So in this lecture, we are going to learn about the batch normalization. So batch normalization is also a regularization technique because it prevents overfitting. Let's see why we need batch normalization. So we know that when we have to pass the data through the model, we normalize the data, but that normalization is for the input layer of the model. But when data travels from the input layer to the first hidden layer, then from the first hidden layer to the second hidden layer, it gets scale due to the matrix multiplication. We know that during every step or during the traveling of data from one layer to another layer, there is a matrix multiplication between the weight of the layers and the features of the data. So due to that matrix multiplication, the data gets scaled. The other reason is that after every layer, we have the activation layer or activation function. So the activation functions are non-linear. For example, the ReLU function is a non-linear because it clips off the negative value. So due to activation functions, the data also get scaled, due to which there is a shift in its variance and mean. To solve this problem, we do batch normalization. Okay, so this is the equation which is responsible for the scaling of the data. So during the data movement or traveling between the layers, we have a multiplication of the matrix. That is, we have a multiplication of a weight matrix and the feature matrix. This multiplication is the first reason of scaling the data. The other reason is that after the multiplication, we have the activation function after each layer. These activation functions are non-linear and they are also responsible for scaling of a data. So let's understand batch normalization more with the help of this neural network. So we have the input layer, we have three hidden layers, and we have the output layer. Before passing the data to the input layer, we normalize the data, then we pass to the input of a neural network. But when data travels from the input layer to the first hidden layer, it gets scaled. Then from first hidden layer to the second hidden layer, it gets scaled because this is the equation which is the responsible for the scaling in each of the layer. So when data travel from one layer to the next layer, then due to this equation, due to this multiplication and this activation function, it gets scaled. So it is the need of the time that we need to normalize the data before passing to the next layer. For that, we need batch normalization. So how to apply batch normalization, or what is batch normalization? So in batch normalization, we normalize each feature independently across the batch. Therefore, in order to see the effect of a batch normalization, we need a large batch. We cannot apply a batch normalization, or we cannot see the batch normalization effect if our batch size is small. Okay. The second point is that we want the data to be normalized for each layer. What does it mean? So it means that for input layer, we normalize the data first and then pass it to the input layer. However, for the hidden layer, we also need to normalize the data. Therefore, we do batch normalization. So we want data to be normalized for each layer. So for hidden layer, we have to do the batch normalization. So these are the other point related to batch normalization. Now, the most important point is batch normalization is only applied during the training. We do not want to apply batch normalization during the testing. There are many reasons. The first reason is that we usually have small batch sizes in the testing time, and small batch sizes are not effective for the batch normalization. Many times we have only one sample in our testing data. So the batch size in that case will be one. Therefore, we want to avoid batch normalization during the testing because we have a small size. Okay, so how we achieve this? So basically, during the testing, when we set our model to the evaluation mode, then PyTorch switch off the batch normalization. So PyTorch does this for us when we put our model into the evaluation mode. So the batch normalization is only applied during the training where we can set large size of batch. When the batch size is small, that is during the testing, we do not need batch normalization. The last point about the batch normalization is that it is also a form of regularization because it prevents overfitting. So in this lecture, we learned about the batch normalization. We see that we want to normalize the data for each layer. And first, we normalize the data before sending it to the input layer of the neural network. But for hidden layers, we also need to normalize the data because when data travel from one layer to another, it gets scaled. So in order to normalize the data for each of the middle layer of the or the hidden layer, we apply batch normalization. For batch normalization, we should select a large batch size. That is, it should be either 32, 64, 128. It is okay. But if our batch size is 1, 2, 4, or 8, these are the small batch sizes in order to see the effect of batch normalization. So I hope in this lecture, you understood the concept of a batch normalization. In the next lecture, we will solve the project on the batch normalization, where we will see the effect of batch normalization on the performance of neural network. Thanks for listening this lecture, and I will see you in the next lecture. Hi everyone, welcome to this lecture. So in this lecture, we are going to solve our project 3 of the section. So basically in this project, we are going to learn how to apply batch normalization on the neural network and how batch normalization improves the performance of a neural network. So here I am in the course material folder. Click on this folder. Inside this folder, I have three major folder of the course. Click on supervised machine learning. Inside supervised machine learning, I have dropout, regularization, and batch normalization folder. Click on this folder. Inside this folder, I have project 3, batch normalization, and then heterodata. So student, basically in project 3, I am going to learn about the batch normalization, and the dataset which I am going to use is heterogeneous human action recognition dataset. If you remember, that dataset was used in the previous section as well, where we designed neural network for the classification problem. So that is heterogeneous data for human action recognition. Okay, click on this file so that we can open project 3 in Google Colab environment. So here I am in my project 3. So for project 3, I need to import few libraries which are torch, torch.nn as nn, torch.nn.functional as f. I also need data loader and tensor data spread. Tensor dataset, I need train test split function as well. I need NumPy, matplotlib, and pandas. Let's run this cell to import all these important Python libraries. Now it's time to check whether GPU is available or not. Let's run this cell. So GPU is available. Let's print the device. So device is CUDA. Okay. Now since I have to use heterogeneous accelerometer, HAR means human action recognition dataset. Therefore, that dataset is present inside the folder. So in order to import that dataset, I need to mount the drive. I need to set the path. Let's run this cell to mount the drive. So the drive is being mounted, and after that, we will set a path of the folder so that we can import our dataset for this project. So the mounting of drive has been done. Let's refresh from here. Then we can see we have a drive. Inside a drive, I have my drive. I have a course material. Inside course material, I have supervised machine learning. Inside supervised machine learning, I have a folder dropout, regularization, and batch normalization. Click on this folder. Inside this folder, I have this data, heterogeneous accelerometer, HAR, or human action recognition data. Since it is present in my dropout, regularization, and batch normalization folder, therefore, from here, I have to copy the path and then I can paste the path here. So let's run this cell. The path has been set. Let's read the data set. Since this is a CSV file, therefore, in order to read the dataset, I am using pandas.read_CSV. So this is the shape of the data. We can see that data has 10 columns. And here we can see that it has about 3.5 million samples. So this is a very large data set. Okay, let's check the first 5 samples of the data set. So we can see that we have 10 columns from index to GT. If we see, many of the columns are not useful, like the arrival time of a user, creation time, then a user code, the model, the device. These are the many columns which are not useful in order to get the performance from the model. So the important columns are only X, Y, and Z. So these 3 columns will be used as a feature. And we also have a last column as GT. So here it is denoted by GT, but it represents the different actions performed by the human. Therefore, these are our labels. Okay, before going further, let's check any null value in the data. So null value is checked by data.isNull.any if there is any null value. So we can see that we have a null value in our last column GT. Since we have 3.5 million sample, a large number of samples, therefore we can easily drop those samples where there are null values. So we are going to write data drop NA, and in place is equals to true, means we want to change them permanently or we want to drop them permanently. Let's run this cell and check only, and now check the null values again. we can say that this is returning false against each column. So there is no null value in any of the column now. Now it's time to get only the important features and the labels. So important features are X, Y, and Z, and the label is present in the column name GT. So I am extracting only those four columns which are important for this dataset. The rest of the columns are irrelevant. And I am calling this as HAR, human action recognition. Let's check the head of the HAR. So this is the shape of our data set now after removing all the irrelevant column. Let's see how many unique values are present in our last column. That is how many different labels are present. So we can write HAR. HAR is our data set now. GT is the last column. And let's check the unique value. So if we see, we have 6 unique values: stand, sit, walk, stairs up, stairs down, and bike. These also are our 6 labels of the dataset. Okay, so we have first label as a stand, then sit, walk, stairs up, stairs down, bike. Okay, now let's check those data samples which belongs to class stand. So here is my dataset, and this is my last column, and my last column has a category stand. So let's pass this as an index to the dataset so that we can get only those samples which belongs to class stand. Okay, let's check the head of those samples which belongs to class stand. So we can see that these are the samples, first 5 samples which belongs to class stand. Let's check how many samples belongs to class stand. So we have here around 0.45 million. So nearly 500,000 samples belongs to class stand. Now student, these samples are very large. If we see the whole data set, in the whole data set, we have around 3.5 millions. So what we are going to do, we are extracting only 5,000 sample for each of the label. So our first label is stand, then sit, then walk, stairs up, stair down, and bike. So what I am going to do here, I am extracting only first 5,000 sample of each class. First, I am extracting it from stand. Let's check the shape of the stand. Now we can see that in a stand, we have a 4 column and we have only 5,000 sample. Do it with all the other labels. That is with sit, walk, stairs up, stairs down, and bike. So I have extracting 5,000 samples from each of the categories now. So I have sit, walk, stairs up, stairs down, and bike. Now it's time to concatenate all these together to form a new dataset which has only 5,000 sample for each category. So I am using pd.concat, stand, sit, walk, stairs up, stairs down, bike. These are my labels. Let's run this cell. Let's see the shape of the dataset now. Now, student, this is our new dataset, or this is our transformed dataset where we have 5,000 sample for each of the 6 categories. So if I multiply 5,000 by 6, I will get 30,000. So we can see that here we have 30,000 now total sample in our dataset. Let's see the dataset now. So this is our dataset now, which has 30,000 rows and 4 columns, where 4th column is the label. Now, student, the last step is for this data set is to replace the categorical values in the label column with the integers. That is, here I am going to do this. I am replacing stand with 0, sit with 1, walk with 2, stair up with 3, stairs down with 4, and bike with 5. Let's run this cell to get these values in the form of integers. And now here is the final and clean form of the dataset which I am going to train my model. So we have 3 features, X, Y, Z, and we have a label column which is denoted by GT here. Now it's time to extract features and label. I need everything in my features except the last column, and the last column will be used as a label. So here are my features. And if we check the shape of the feature, now I have 3 columns in the feature and total 30,000 sample. Here are my labels where I am only using column -1. Here I am using every column except the last column, which is -1. So -1 is the index which denotes the last value. Okay. So y dot shape is 30,000. So I have 30,000 label for each of the sample here. Now, after extracting features and label, it's time to perform the train test split. So for train test split, I am going to use 20% data as a test and remaining 80% data as a training data. Let's perform train test split. Now transform to tensor and using data loader. So in this 4 lines, I am converting my training data, train labels, testing data, and testing labels into PyTorch tensors. Okay, now here I am converting to PyTorch dataset. PyTorch dataset means that I have transformed those training labels, training data, testing label, and testing data into tensor dataset. Okay, after tensor dataset, I will push these tensor dataset into the data loader. And here I am using a batch size of 64. If you see, I am using this batch size only for the training component. If you see, I put batch size is equal to batch size only for the training data load. For data loader, I am passing all the samples at once to the model. If you see here, the batch size is test underscore data dot tensor dot 0 dot shape. In that case, I am passing everything at once to the data loader. So for batch normalization, or to understand the batch normalization, I did not divide the test data into the batches. The whole test data will be passed at once through the model. Okay, let's run this cell to perform these steps. Now observe the batches of training and test data. So if I apply for loop in a train loader and I break it just after one iteration, what I will get? So we can see that I have 64, my batch size, which I have defined here. And here I can see that the three are my features. So the batch size is 64 and I have 3 features. Also, I can see that we have 64 labels. So batch size selected here is 64. Let's print y here. So if we print y here, we have these 64 values of y. Now it's time to check test loader. Since I am not applying a batch size on a test loader, therefore, what I have done here is I am using a function next, then iter test underscore loader. If I run this cell, I can see that all the 6,000 samples which are present in a test loader will be considered here. So in this case, we can see that we did not divide test data into any batch size because we have total 30,000 sample and we are using 20% as a testing. So 20% of 30,000 is 6,000. So these are our total testing samples. Okay, now it's time to create the neural network. So here I am going to create the neural network using sequential method. So it start with 3 because the number of feature in our data set are 3. Then the second is 64. I have a ReLU layer. Next hidden layer is starting from 64. Then the other hidden layer is starting from 32. Then the last layer, which is also a classification layer, starting from a 16 because previous layer ends at 16. Then here is a 6. This 6 is my number of classes in a data set. Let's run this cell to create the model. Now it's time to train and test the model. Now I am training my model for 101 epochs. So this is very, very standard code, which now we have seen many times how to train and test the model. Here is my loss function. This is my optimizer. Here I am moving my model to device, that is GPU. These are my initialization, that is losses, training accuracy, and test accuracy. Here I am starting my for loop for epoch. I am putting my model to the training mode. This is my batch loop. I am training the model with batches where the batch size which we have set is 64. Okay. After the training, the testing will be start. For testing, I will put my model to evaluation mode. And here I am passing all the test sample to a model in one iteration. Therefore, the command is next iteration test underscore loader. We have already seen this before. Okay, here we have seen this. Next is to calculate the test accuracy. So we can see that the training has been started, 70 epochs have been passed, and we can see that we started with a loss of 0.9, and now we have reached up to 0.53 after 80 epochs. So the loss has decreased after 80 epochs. After 90, we are still at 0.53. So here we can see that our training has been completed, including 0 and 100 epochs. We have total 101 epoch. So our loss is 0.49 here. Now it's time to go for plotting and visualizing the result. Okay, let's run this cell. So we can see that our accuracy is 79%, both with training and testing. Approximately same. There is slight high accuracy with training, that is 79.75, and the testing accuracy is 79.15. So this is the performance of our neural network on this heterogeneous human action recognition dataset without batch normalization. Now it's time to create the model with batch normalization. For batch normalization, I am going to use a class in order to create the model. So the name of my model or the class is classifier here. First, this is my input layer. So this is the same. That is, it start from the number of feature and the end with the 64. This is the output feature of our input layer. These are my hidden layers. If you see, the first hidden layer is starting from 64 because the output features in the input layers were 64. So the next layer will start with the same input feature which other has as an output feature. Okay, so here after first here for first fully connected layer, I am applying batch normalization. If you see, I am passed 64 as an input to the batch normalization. This is because the input feature size of fully connected layer is 64. So this layer will perform batch normalization for the data which will travel towards the first fully connected layer. Then I have a second fully connected layer. If you see, for second fully connected layer, I have batch normalization where I pass 32 as an input to the batch normalization. And here I can see this 32 is because of the fact that the input features in our second fully connected layer is 32. So we are applying batch normalization for our hidden layers, which are the fully connected layers. Okay, so for first hidden layer, we are normalizing with respect to the input feature of FC1, that is the first fully connected layer or the hidden layer. And for second fully connected layer, our input is 32, which is the input feature of the second fully connected layer. So in this way, we can see that for the layer which we want to normalize the data, we have to pass the number of input to the our batch normalization layer. That input should be the same as that of input feature of the fully connected layer or the layer to which we are going to apply the batch normalization. So we are applying batch normalization only for these two hidden layers. This is my output layer. We can see that it starts from 16 because the previous layer ends at 16 and it has a 6 at the end because this 6 represents the label or classes in our data set. This is my forward function. Here I am passing the data through the model. First, the data will be passed to the input layer, then it will pass to the ReLU layer. After passing to the ReLU layer, we are normalizing it for fully connected layer. Then it will pass through ReLU after the first fully connected layer. Then we again performing batch normalize it. Then we are passing it through our second fully connected layer. And after that, we are passing it through our ReLU layer. And finally, it is passing through our output layer. So this is the creation of the neural network with the help of a class, and we are using now batch normalization with our model. So let's run this cell to create the model. Here I am creating the instance of the model and I am calling it model2. This is the name of the class for which I have designed my model. So I have to create the instance of the model with the name of the class. I am calling the model as model2. Now here I am starting the training and testing of the model for the same number of epochs so that I can clearly see the effect of batch normalization. If you see, rest everything is same except the fact that now I am calling my model as a model2. So model 2 is the neural network with batch normalization. And if you remember, model was the neural network without the batch normalization. So here, this is the same training and testing code, exactly the same, which we used here and which we used in our previous projects and also in the previous section, which was neural network for the classification. So if you see, I have used model 2 now everywhere. Here I am putting my model to device. Here I am putting my model to the training mode. Here I am initializing the batch accuracies, the losses, and here I am going to use to perform a training in batches. This is my batch loop. Again, I am passing my data for a training. I am getting prediction, calculating loss. We know about these three steps. They are for the back propagation. And here my batch loop completed. And now I am out of the batch loop. So finally, I am calculating my losses and training accuracy. Okay, now here my testing has been started. So I am putting my model to evaluation mode. In the previous lecture, we learned that when we put my model in evaluation mode, then it doesn't perform the batch normalization because we need batch normalization only during the training. We do not need batch normalization during the testing. Here I am passing, uh, uh, extracting the number of testing sample from test loader. And here I am passing the testing samples from the model to get the prediction. So this is exactly the same code which now we have seen many times. First time we studied this code in the previous section when we designed neural network to perform classification on the MNIST data. Okay, so the training has been completed after 100 epochs or 101 epochs basically before, because if I include the 0 epoch and the 100 epoch, I have 101 epochs in total. Okay, so the training has been completed for the batch normalization. That is the model which has batch normalization layers. Now it's time to plot the performance. So when we plot the performance, we can see that our training accuracy is now 81.43 and test accuracy is 81.18. If I go back, we can see that without batch normalization, I have these values. I have 79.75 and 79.15. After batch normalization, we can see that our accuracy has slightly increased. We have around 1.5% increase in the training and testing accuracy of the model. So in this project, we learn how to use batch normalization. The most important thing we learned is how to write a code for a neural network having batch normalization layer. We can see that here, when we apply a batch normalization to a particular layer, so the input to our batch normalization function should be equal to the number of input feature of that layer. When we apply batch normalization, we obtain slight increase in the performance of the model. So in this lecture, we learn about the batch normalization. We observe that there is slight improve in the performance of a neural network when we use batch normalization with the neural network. So I hope you understood the concept of a batch normalization. I hope you understood how and where to apply batch normalization in coding. I hope you understood this lecture completely. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. So in this lecture, we are going to solve our project 4 of this section. So basically in project 4, we are again going to apply batch normalization, but this time we are going to use a different data set. That is a custom image data set. So this is the same data set which we use in our project 2 of the section as well, where we learn about the dropout regularization. So here I am in my course material folder. Click on this folder. So inside the folder, I have introduction, supervised machine learning, and unsupervised machine learning. Click on supervised machine learning. Inside supervised machine learning, I have a folder, dropout regularization and batch normalization. So click on this folder. Inside this folder, I have my project 4 batch normalization on custom images. Click on this file so that we can open it in our Google Colab environment. Now, student, this is a custom image dataset. As I already told you that we have used this dataset in project 2 of this section. And we have already used this dataset in the previous section of the course, which was about neural networks for classification. In that section, we learn how to design neural network for custom images. Now, student, in order to save time, I am not going to run this project here. So basically, this project I have already run. So I am going to explain you only that part of this project, which is new. So if you see here at the start of the project, I have installed split folder. The reason is that I am using a custom image dataset. So for custom image dataset, we have images in the folder and we cannot split the data using regular train test split function. We need a split folder function in order to split the function into the training and testing. So with this cell, I have already installed this split folder function. Okay, now these are my libraries. I have imported torch, torch.nn as nn, torch.nn as functional as f. Then I have imported data loader and tensor dataset. I have here importing split folder that I will use to split the folder into training and testing. Okay, now I use NumPy. I know I need pandas. I need matplotlib. So these are the libraries which I am going to use in this project. Here I have checked that the CUDA is available, that is GPU is available for our project. Here I am using transforms.compose function in order to transform my images into PyTorch. Also, this function helps us to normalize the images. Here I have mounted the drive. Here I have set the path, and here with the help of mounted drive and path, I have read the data. So there are a lot of things which are going on in this particular cell. My data is circle underscore cross, and here I am creating an output folder. Now, student, you have seen this many times. You have seen this in the project 2 of this section as well. Okay, I am splitting this folder into 0.8 and 0.2, that is 80% data will be used as a training and 20% data will be using as a testing. Here I am transforming my training and testing component into the tensor dataset. Since the images are in image folder, so this is the way to transform the image folder both for training and testing into the tensor dataset. Here I am using my data loader. So the batch size is 32 for each of the train loader and the test loader here. Okay. So if we see, this is our data set. So now you have seen that we have used this data set many times before, especially we have used this in project 2 of this section as well, and also in the previous section of the course. So we have two classes in our custom image dataset, that we have crosses and circle. Okay, now it's time to create the model. And first I am going to create the model without batch normalization layer. Since if we see here in our data loader, our image is 4D. So the size of the image is 116 by 116. So this is the 4D, four-dimensional data in a train loader. And when we use that data for our model, we will have to transform that data into 2D. So this is the size of our image. This is the channels of our image. Our image is 3 channel, that is a color image. And this is our batch size. Okay, so our image has 116 by 116 size, and it has 3 channel. Therefore, if I multiply these 3 things, I will get 40,368. So this is the features from which my designing of neural network will start. Then I reduce the feature to 2048, and then here my second layer or my first hidden layer has been started. This is my second hidden layer. This is my third hidden layer, and I have reached to my final layer. In the same way, I am placing the different number of features, and every time I am reducing the feature. If you see at the end or at the output layer, I have only 64 input feature, and finally I have 2 here. This 2 shows the number of classes, because we have 2 number of classes, that is we have cross and we have circles. Okay, now the model has been created. Now it's time to train and test the model. So I am running it for 41 epoch. The rest of the code is exactly the same. Here you can see that I am reshaping 4D data to 2D. The reason is I am using train loader, and if we see the train loader has a data in the form of 4D here. These are the 4-dimensional data. So what I have done is I have combined the last 3 dimension. I kept my batch size and I combined the last 3 dimension. So it will return 40,368 that I am going to use here. Okay. So when I complete the training and testing of the model without the batch normalization, I can see that my accuracy is 96.88% on the testing data, and training accuracy is 90.24. So these are the values without the batch normalization. This is my training. We can see that for a large number of epochs, approximately 25, the loss is not dropping much, and after that it drops, then rise it again, and it drop again, and we reach up to the training accuracy of 90.24 after 41 epochs. Okay, now it's time to create the model with batch normalization. Now this is the same model, except we have added the batch normalization layer for each of the hidden layer. Okay, this is my input layer. So I started with the number of feature, then I have 2048. Now my first hidden layer, which is also a fully connected layer, is starting from 2058 because that is the output feature of the input layer. And it also ends with 2048. Now for this hidden layer, I am using a batch normalization layer. So I am passing the input 2048 to my batch normalization layer, which is same as that of the input feature of FC1. Now the input feature of FC2 is also 2048. Therefore, for second batch normalization, I have to pass 2048 as an input parameter again. Now the third FC3 start from 1024. So the input feature for my third hidden layer is 1024. Therefore, in order to perform the batch normalization for this layer, the batch normalization for this layer has input 1024. So the input to the batch normalization layer is always equal to the input features of the layer for which the batch normalization layer will be used. Then I have fourth fully connected layer, and its input features are 512. Therefore, for this layer, my batch normalization layer has 512 as input. This is for the fifth batch normalization layer, and this is for the sixth fully connected layer. So I have 6 fully connected layers as a hidden layer in this deep neural network, and therefore I have 6 batch normalization layer. This is my output layer, and output layer start from the output feature of the previous layer. And this is my final output feature of the output layer, and it is 2, which represent the number of classes in the dataset. This is my forward pass through the layers. We can see that first I pass the data to the input layer, then I'm taking the ReLU as an activation. Then the first batch normalization layer, the data will pass, then it pass through FC1, then again through the ReLU function, which is an activation function. Then the data will pass through the second batch normalization layer, and then it passed to the second fully connected layer. Similarly, this is data which is passing through each of the batch normalization layer and then the hidden layers. And finally, we reach to the output layer and we are returning the data. So here the data has completed the forward pass through the whole model, that is from the input layer to the output layer. Now here I am creating the model instance. Since I have created the model with the help of a class, and I am calling this class as a classifier. So therefore, here I am creating the model instance. The name of the model is model2, and I am creating the instance from my class, which is classifier. Here I am training and testing my model2, which is the model with batch normalization. So here everyone you can see model2. Here I am putting the model2 in the training mode. Here I am pushing the model to my GPU. Here I have starting the training in batches, and after I have putting my model in a testing mode. For that I have put model into the evaluation mode. So evaluation mode here basically deactivates the dropout as well, since we did not apply the dropout here. So basically it deactivates the gradient, and also it will deactivate the batch normalization, because we do not need batch normalization during the testing. Okay. Now After completing the training on 41 epochs for the model which has the batch normalization layer, I can see the model performance. So here the model performance has been improved a lot. We can see that we have a training and testing accuracy of 100% after 41 epochs. If we see the losses here, we have almost reached the losses which are very, very close to zero. This is a very tiny value of the loss, due to which we can see that we have reached up to the training and testing accuracy of 100%, which is better than the previous performance of the model, where the training and test accuracy was 90 and 96.88% respectively. So student, in this lecture, we apply batch normalization on a totally different data set from the previous data set. In our project 3, we apply batch normalization on a human action recognition data set, but here we are applying on the imaging data set, that is on a custom image data set. We see here we have large number of hidden layers. We have input layer, we have 6 hidden layers, and we have output layer. We apply batch normalization to each of the hidden layer, and we can see that with the help of batch normalization, we are able to get the improved performance from the neural network. So I hope you understood this lecture very well. Thanks for listening, and I will see you in the next lecture.